Good day, seniors. In this lesson, we will graph a higher degree polynomial, this polynomial, using concepts of curve tracing. Okay, so the function given is x cubed over 3 plus x squared minus 3x minus 9. The first step is always to get the special points of the curve, mainly the roots, points, maximum points, minimum points, and the pi, or the point of inflection. Now, let's solve first for the roots of this polynomial. Of course, to solve for the roots or the zeros of a polynomial f of x, we simply need to equate f of x to 0. So equating this to 0, we have x cubed over 3 plus x squared minus 3x minus 9 equals 0. So multiplying by 3 to make our solving easier, so you have x cubed plus 3x squared minus 9x minus 27. Now you can solve this polynomial using your methods, but I like to solve polynomials by factoring if I can. And here I will use factoring. X cubed plus 3x squared. I'll just group the first two and then group the last two and factor this by grouping. So the common factor in the first group is x squared, leaving you with x plus 3. Now the common factor in the second group is 9, to give you x plus 3 equals 0. So you have here x squared minus 9 times x plus 3, which is equal to 0. So x squared minus 9 is of course x plus 3, then x minus 3, factoring it, difference of two squares multiplied by the other factor x plus 3, 0. So we have now the values that will make the function 0, and those are negative 3 for this factor and this factor, and then 3. So obviously the roots of the polynomial are the points negative 3, 0, and then 3, 0. Of course, when you substitute this negative 3 and 3 back to your function f of x, you will get 0 since we solved it for 0. So the points or the roots are negative 3, 0 and 3, 0. So now we know the roots. Now let's solve for the maxima minima, the points, maximum points or minimum points of the function. Okay. In solving for the maximum points or the minimum points of the function, we need to equate the first derivative of the function to 0. So we need to get the derivative first. X cubed over 3 would be x squared. The derivative is x squared. Derivative of x squared is 2x, and the derivative of negative 3x minus 3. And equating this x squared plus 2x minus 3 to 0 by simple factoring, since this is factorable, so we have x plus 3 and x minus 1 to 0. If you have a quadratic that cannot be factored, you can always use the quadratic formula. So now you have the values that will make the first derivative 0, and it's negative 3 and 1. But remember that these are points or ordered pairs, so we need to substitute these values, negative 3 and 1, to our original f of x to get the y coordinate. So you substitute negative 3, this will become negative 3 cubed, or negative 27 over 3, that's negative 9, plus negative 3 squared, that's 9, so negative 9 plus 9 is 0, minus negative 3, that's positive 9, minus 9, get 0. Remember that negative 3, 0 is also a root, as we have solved earlier. And if x is 1, this becomes 1 cubed over 3, or 1/3, plus 1 minus 3 minus 9. 1 minus 3 minus 9 will be minus 11. So this is 1/3 minus 11, which will give you 1 minus 33 over 3, or negative 32 over 3. Negative 32 over 3. So the points negative 3, 0 and 1 negative 32 over 3 are maximum points and minimum points of the function. Obviously the point 1 negative 32 over 3 is a minimum. And now we have obtained the maximum minimum points. Yes. Now lastly, the point of inflection. The point of inflection of a graph of a function is where the sense of concavity of the function changes, and it can be obtained by equating the second derivative of the function to 0. So remember that the first derivative earlier is x squared plus 2x minus 3. So the second derivative would be 2x plus 2. And this is what we will equate to 0. Solving for x, x is simply negative 1. Again, this is a point, an ordered pair, so you need to substitute your x value to the original f of x. So you will get here, substituting negative 1 to the function, you get negative 1/3 plus 1 plus 3 and minus 9. So you get here negative 1/3 minus 5. So this is simply negative 16 over 3. So this is negative 16/3. So this is the point of inflection. So and now we know the special points. All we need to do is to plot them. So let's plot the roots first. Negative 3, 0 would be here. Okay, the point 3, 0 is here. Maximum points represented by these blue dots. 1 negative 32 over 3 would be, this is 1 negative 32 over 3 is close to 10. No, negative 10 and 2/3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2/3, somewhere here. Then the other point, negative 3, 0, is also a root. So that's why let's just put it there. It's also a root. Now the point of inflection, negative 1, negative 16/3. Negative 1, I'm sorry, 1 negative 32 over 3 would be in the right side. Yeah. And then negative 1 and negative 16 over 3 would be, negative 16/3 is negative 5 and 1/3. So 1, 2, 4, 5, somewhere here. So now we have plotted these special points of the graph. The next thing to do is to study the behavior of the functions, meaning to apply the derivative test. Now these are the points we obtained earlier. I already plotted it. Now notice how these points will divide our number line, our Cartesian plane, into intervals, into regions. So this interval, the shaded one, represents all values from negative infinity to negative 3, the first special point. The next interval would be from negative 3 to the next special point, which is this point, negative 1. So you have the interval negative 3, negative 1. Then the next interval would be from the negative 1 to the next special point. So from this point to this point, the region in between, represented by negative 1, 1. The next interval would be from 1 to the next special point, which is 3, this point. And this is the interval between 1 and 3. And lastly, the interval from this point towards positive infinity. So this plane, this region, and this is of course the interval positive 3 to positive infinity. Now remember, we can test for the behavior of the function in every interval using the derivative test. Let's recall the first derivative test. The first derivative test says if the first derivative of a function, of a value, is positive, then the function is increasing. And if the first derivative is negative, the function is decreasing. Now all we need to test here in our intervals is only the first. No, let's just use the first. So let's just, anyway, once we have the behavior of the function in the first interval, we can simply follow the points as we go along and then graph it. So the first derivative test will tell whether the function increases or decreases in a given interval. And then the second derivative test would be a test to determine whether the function is concave upward or downward in an interval. If the second derivative is positive, then the function is concave upward in that interval. And if it's negative, the function is concave downward in the interval. Now, we have to test this interval, negative infinity to negative 3. So obviously, we try the value x is equal to negative 4. It is in that interval. So substituting negative 4 to the first derivative, so what is f prime of 4? So f prime of 4 would be negative 4 squared, that's 16, minus 8, minus 3. So that's 16 minus 11, and it is equal to 5. So f of negative 4 is 5. And the first derivative is positive. That means the function is increasing in this interval. Increasing. Okay, and testing for the second derivative, f prime of negative 4. Using the second derivative, so negative 4, 2 times negative 4 is negative 8 plus 2, f double prime of negative 4 would be negative 6. So that means the function is concave downward in the interval. Concave downward. Now we know the behavior of the function from in this interval. All we need to do is to see the behavior So if it's increasing in this interval, in the first interval, that means we have to start from below the point and increasing in a concave downward manner is how we do that. And then going from this point, knowing that the blue point is a maximum point, there's no way to go but down to the red point. And remember that the red point is a point of inflection. So we are still concave downward up to that point, right? Just like that. And from this point going to the next point, which is the blue point, obviously we need to decrease. The function is decreasing in that interval, but this time we are now at the point of inflection, so the concavity must change. It should now be concave upward. So notice that this is concave upward. And remember that this blue point is a minimum point, therefore all we need to do is to go up so that the blue point is a minimum. Therefore, from the blue point to the next special point, we need to increase. And the concavity is obviously upward also because there's only one point of inflection. Remember, we are concave downward up to this point, and then only after this point, the concavity will change. And from this point on, the concavity is upward. So this is how basics of concepts of curve tracing used in graphing higher degree polynomials. Good day.